So last time we set up this square loop of current and we looked at the magnetic field kind of going around the loop. This time we want to get a little more quantitative and look at the magnitude of the magnetic field as we get farther away from the center of the loop. So I want you to imagine a line of observation points starting here at the center of the loop and pointing out perpendicular to the plane of the loop. This is going to be our y-coordinate that will be increasing, and we want to look at how the magnetic field changes as we get farther away from the center of the loop. So our geometry is the same as last time. We just need to set up these different observation points and set up a graph to be able to look at the results. So here's our geometry again. We've got a square. This time I'm going to control the size of it with this side length variable. Before I was manually putting that in and that became difficult to change. I'm also setting the current for the loop here because they're all going to have the same current value. We're not going to have it branching off into different wires. So these two are going to control the size and the strength of our current loop. If I scroll down, we've got our current arrows. Those again are just for visualization, not really helping us in the calculation. Here we are finding the center of the set of wires that make up the loop. And then here we've got the locations that we'll be observing the magnetic field at. To set this along the center of the loop, we use XS and ZS as the X coordinate of the center of the sources and the Z coordinate of the center of the sources. And then we're going to be moving Y along from 0 to 20. Actually, we're not going to go quite all the way to 0. We're going to go to 10 to the minus 6 so that if we need to, we can go to a logarithmic scale on the horizontal axis. You cannot have a 0 or a negative in the data set for a log scale. And so here we're setting our locations up. We've got our XS, YS, ZS. So these are the basically the X and Z are kept constant, and the Y is going to move up along the Y axis. And then here we calculate the magnetic field. We start out with 0. We add the magnetic field for each of the source wires in the loop, and then we graph the magnetic field magnitude versus the y-coordinate that we're located at. So this is the distance from the center of the loop, and this is the magnitude of the magnetic field. Now, the magnetic field is only going to be pointing in the z direction, so we're not losing any information by just graphing the magnitude. So when we run this, here's our loop in the XZ plane. I'm going to right-click to rotate so that we can confirm, yes, this thing is going around this way. So our magnetic field is going to point actually along the negative Z-axis by doing the right-hand rule, but we could just flip the current around and it would point upward. It'll have the same magnitude. Or I think I can flip, yeah, I can flip this thing around. Maybe I can't get it quite all the way flipped around. Okay. Anyway, let's scroll down to the graph. So here we've got the magnetic field versus Y. You can see it dies off pretty quickly. So the length of a side of the loop is 1. So by about the time we get to 2 times the length, we're pretty much close to 0 compared to the original value here at the origin. We also notice it's got this little cap to it here. So it's approaching a maximum here. So it's concave up as we get closer to the ring and concave down as we get closer to the ring and concave up as we get farther away. That is one of the most confusing terminologies I've ever encountered in mathematics. I know it makes sense, but for a maximum to be concave down, my brain is still trying to wrap itself around that concept decades after I was in college. But anyway, we have a concave up, excuse me, still doing it. Concave down here, concave up here, which means at some point in the middle we have an inflection point, which is pretty cool. So here's a real life example of an inflection point. And so the question becomes, what controls the shape of this graph? What controls the height of it and what controls the width of it? We've got 2 major things we can play around with. We've got, like we saw before, the side length and the current. Let's try the current first. Let's up the current by 10. So this is where you have to kind of keep this graph in mind. So we are looking at a graph kind of shaped like this. And then when I hit Control 2, it's going to be replaced by a more powerful current. Wow, that is an impressive looking current. But you notice the graph doesn't change all that much. The width is the same, but the height of the current the height of the magnitude increases. So we see that the current controls the height of this graph, which makes sense. The stronger the current, the stronger the magnetic field, but it doesn't really have an impact on the width of it. The only thing that's going to control that, let's delete this 0 to get that back to normal, is if we increase the side length. So now we're going to increase the side length to 10. So we're increasing it by a factor of 10. So you notice we now have this long, thin-looking loop of current. It only looks thinner because the radius of the wires was kept constant. If I scroll down, you notice the height remains about the same as it was before, but we now have a much broader curve to this. So you see, we've got previously we were dying down at about 2 units. So now up to about 2 units, we've only gone down by this much. Now, of course, we have to think of in terms of the scale of the side length. So we were pretty much died down at about halfway. Here, when I get to half of the, excuse me, I need to go to 2 times the side length, don't I? Yeah. So by the time I get to 2 times the side length at 20, again, I'm close to back down to 0. So at about 2 times the side length away, we approach 0 pretty closely. Now, of course, I can get more information off of this graph if I make it into a log-log plot. Let's go back over to here, and now I'm going to uncomment this line so that it becomes a log scale on the y-axis, a log scale on the x-axis. Let's leave the side length at 10 for now. Let's just see what it looks like. Cool, so this is the same data, just on a log-log plot. Here's that maximum, so it looks very flat here, but you get an idea of what's happening with our data points here because I've turned on the markers feature in the new GlowScript 2.7. So you see we're doing linear spacing here on a logarithmic scale, but it gives you an idea of how flat this thing becomes as you kind of approach but never reach 0. And you see here we're starting to get a straight line, which indicates a power law on a log-log graph. So let's Alt-Tab back over to here. Let's decrease our side length so that we can get a little bit more of that power law in the window. And here we get more of that straight line. So this is telling me it's falling off like a power law. I know that for the ring of current, so if you take this and change it from a square into a circle, this goes like the -3/2 power. I'd have to double check for whether it's doing that here. But the important thing is we're getting a power law just like you get for the ring of current. Actually, no, don't listen to past Brian. Future Brian is right. There is a 3/2 power, but it's the variable squared to the -3/2 power with this thing added in. So as you get farther and farther away, you ignore this this radius of the ring, and so it ends up being z squared to the 3/2, so that becomes 1 over z cubed. So it's actually going like 1 over y cubed as you get farther away, or pretty close to it. I think it works out the same for the square as it does for the ring. Anyway, just wanted to issue that correction. Thank you so much for your time. I will see you next time. Bye-bye.